All right, mic check one, two. Good afternoon, ladies and gentlemen. Good evening. Welcome to another series of tutorials with me, Aubrey. This is going to be a very interesting lesson, even as we start. All right, even as we start, don't forget to subscribe to the channel. Help the channel get to 1,000 subscribers. Let's do this together. Our projections should be by the end of August that we get to 1,000 subscribers. All right, we get to 1,000 subscribers. All right, so let's dive into this. So we are doing the Cauchy's theorem. All right, we are doing the Cauchy's theorem. We're doing the Cauchy's integral theorem. Sorry, the integral theorem should not be confused with the Cauchy's theorem. All right, we're doing the Cauchy's integral theorem, which says that if f of z or if f of z is analytic everywhere except at C in a region mu. All right, so there is this region mu, and this f of z is analytic everywhere except at the point C. All right, and if it so happens that we can draw a circle around C, C is an element of this circle, okay, where C is the center. If it so happens that we can draw a circle around C, then the integral of f of z over the point where it is not analytic with respect to z is equals to 2 pi I f of c. All right, so this is Cauchy's formula, integral formula. It should not be confused with Cauchy's theorem, all right, which we previously proved. I'll link that in the description below. So, but this is Cauchy's formula, and we'll be looking at this. All right, let me just explain what this implies here. All right, so this implies here, what this implies here is that if we have a region mu where this function is not analytic at C, but it is analytic everywhere, and if we can draw a circle around C, let me just draw a circle around C. If we can draw a circle around C like that, with radius r, okay, we can draw a circle around C with radius r like that, then what we are going to have is the 2 pi I f of c. All right, let's head on with the proof. Let's head on with the proof. All right, proof. So we start with the left-hand side here. We start with this very equation here. We write it down and we equate it to itself because they are the same. We equate it to itself. Okay, with respect to C, that's where the proof starts. Now, what we're going to do is our goal is to try to introduce f of C, which is the function of C, which is here. All right, but we don't have to change the meaning of this statement. So how can we introduce f of C on top here without changing the meaning of the statement? So what we can do is we can say this is f of like that over z minus C with respect to z like that, so that this and that can cancel out because they are additive inverses of each other, and we'll still get back to that. All right, so what we'll do further here is we're going to separate. We want f of c alone, the positive part of f of c alone here. So we are going to separate that. All right, separating that, we're going to have that, something like that, with respect to z, like that. Hope it's clear up to here. All right, so from here now, we see that z minus c is just a complex number. All right, this can be a complex number. It will have a real part and an imaginary part. And whenever we have a complex number, we can always write it in polar form. All right, so this z minus c can always be written in polar form like this. All right, and getting the z with respect to theta here, and how we know that we are doing it with respect to theta, okay, with respect to theta is because we have 2 pi here. 2 pi meaning that we have 2 pi here, meaning that there is a form of theta that must have been gotten from the explanation. So we differentiate this with respect to theta, all right, and make the z the subject of the formula. Okay, we're going to have that. Okay, so the goal here is to change this into theta so that we can integrate from 0 to 2 pi because theta always runs from 0 to 2 pi. Let me just do that. Let me explain that. You just see that as we'll be solving. So what we can do next here is that we can introduce f of z both sides of this equation. We introduce f of z here, introduce f of z here, and we're going to have f of z minus c. But we know that f of z minus c can be written as f of z minus f of c. So f of z minus c can be written as f of z minus f of c. Okay, and we introduce f here, so we're going to have that there. All right, and we see that this is equals to this, and the z is equals to this, and this, which is this, is equals to that. So we can replace that, and we're going to have the integral like that, e to the I, the theta like that, plus like that, okay, like that. And what we've just done here is just introduce. Um, we've just introduced, we've introduced, we've replaced where there is dz, we replace with that, where there is z minus c, we replace with that, and so on and so forth. All right, where there is this, we replace this. All right, and now what we're going to do is we see that there are some items that can cancel out there. All right, so we can cancel out some items. So here we're just going to remain with that, and there we're just going to remain with that. Okay, so we're just going to remain with that there. What we can do is we'll get back to our contour. We say that since our function f of z is analytic everywhere in this contour except at this point C, and it so happens that we can draw a circle around C. Okay, okay, it so happens that we can draw a circle around C. Now I want you to concentrate on this. Now we don't want this circle, we want this contour here. This is the original contour. So what if this circle becomes smaller and smaller as we are approaching C? So what happens if this circle, or what happens to the radius, okay, what happens to the radius of this circle as it becomes smaller and smaller as it approaches C, so that we have completely just a C there. So what happens, as we can see, is that this radius becomes or approaches 0. Okay, let me repeat that. So as the radius is approaching C, because we want this form, we don't want the circle here, as the radius is approaching C, okay, as it is approaching C, the radius is decreasing and the radius is becoming 0. So as the radius is approaching C, the radius is equal to 0. So now what does that tell us? So it tells us that where there is arrow, we can put 0, okay, and this part will be 0, and the only part that will survive is this part. So we can say this is equal to, okay, that. So this part is 0, no need to write that. So this 0 times everything here will make this to be 0. What we just remember is this, which we have here. And we can integrate that with respect to theta. Okay, since there is no theta term there. So this is just theta f of c, and the limits from 0 to 2 pi, like that. All right, so from here, what we're going to do is we replace the upper limit. Then later we replace the lower limit, of which it will just be equals to 2 pi I f of c. And proved. Okay, those that are behind, this is the original part. This is the left-hand side part that we already have. And this is after we replace the upper limit, we're going to have 2 pi I. And the lower limit minus will just be 0, everything here. Hence showing that this part is equal to 2 pi I f of c. All right, you can always go back to the video and watch through anywhere you didn't understand. And if you have any questions, you can just leave them in the comment box. So if you have any questions, leave them in the comment box. Leave them in the comment box like that. So yeah, I will be able to respond to your questions. So this is Cauchy's integral formula. Cauchy's integral formula. Remember to subscribe to the channel and help the channel get to 1,000 subscribers. Have a good day.